This video is for Tuesday evening, yesterday. That was for today in class, but you were off at the senior meeting. Section 4.4, the second fundamental theorem of calculus. Your homework from this is section 4.4, 81 through 92. So here is, in a nutshell, the second fundamental theorem of calculus. First off, it is here. First off, look at this. This is my original function. When you take the first derivative, it is here. And then when you integrate it, you're going backwards, right? Notice things like this is t, this is x, and this is some constant a. So after I take the antiderivative, I would go from x to a, maybe like from 3 to 4, who knows what it is. But this is the second fundamental theorem of calculus. Take a look at this piece here. So if I go and I integrate this function, I go back to the original. And then if I take the derivative of the original, I go back to this. So this is the first derivative. This happens to be the same as this, except this function is with t and this function is with x. This is this circular argument that I would do in geometry. If two triangles are congruent, let's see, how do I say that? When segments are congruent, then they're also equal in measure. If they're equal in measure, then they're also congruent. If they're congruent, they're equal in measure, etc. That circular argument. Well, same thing here. This undoes, these two undo each other. Again, look inside of here. That when I take the antiderivative, like this is like the first derivative, this is like the velocity. I'm going to go back to the original. Then the output to this is the original. I'm going to go back and take the first derivative. So I go back to this. So it's a circular argument. So the first derivative, which is the same as what's inside of here, because when so anyways, how do I find this? When you see something like this, when they tell me to find this and I have to do this to it, here's the second fundamental theorem of calculus. What you do is you take this function and you substitute it for the upper bound. It just happens to be x here. It could say x squared plus 2. You put x squared plus 2 in for everywhere in the variable in this function. So again, how you solve this by the second fundamental theorem of calculus is you take this function and you substitute in the upper bound times the derivative of the upper bound with respect to x minus, I take my function again and I substitute in the lower bound. Times the derivative of the lower bound with respect to x. So I'm going to kind of treat this like a discovery problem. Oh. There we go. So I give you, again, let me take it down here. Here is like my first derivative, and when I integrate it, I get my original function, right? And then after I go and I get this original function, you really want me to go back and take the first derivative, go back to this? Except this time it's going to have x's in it instead of t's. Well, I'm going to do it the long way first by not worrying about the second fundamental theorem of calculus, and then I'm going to go ahead and use it. So I'm not even going to show that second fundamental theorem of calculus right now. Let's just go ahead and do what it says. So the first thing I better do is I better find f of x, then I can go take the first derivative. How do I find f of x? I'm going to go ahead and integrate. Well, that we know how to do. Well, that's I raise the power and divide by that power, minus I raise that power and divide by that power from x to negative 2. I simplified it, 1/3 t cubed minus t squared from x to negative 2. Now I put in x here, minus, now I'm going to put in negative 2, and then I continue to clean this up, right? Negative 8 over 3, that's a positive, that's a positive 4, but it has a minus here, right? I got to get a common denominator now of 3, so that'd be a negative 8 minus 12 all over 3. So that just kind of sits there, and then I distribute that negative to the negative 20 over 3 inside. So there is my f of x. What did they want me to go do? Find the first derivative. So go back now and take the derivative of this. Well, now I bring down, I leave the 1/3, I bring down the 3, I reduce that power, minus, bring down that exponent, reduce that power, and that constant goes to 0. My first derivative is x squared minus 2x. I did this the long way, the only way we know how to do. Now I'm going to apply the second fundamental theorem of calculus. Messed up, sorry, I used a pen. So define the first derivative directly. So that is taking the derivative of the integral. Again, this is like the first derivative. When I do the integral, that goes back to the original. Then you want me to take the original, go back and take the first derivative. And how did it tell us to do this? It told us to take this function and substitute in the upper bound. Wherever I saw the variable, I did, times the derivative of the upper bound, minus take this function, substitute in the lower bound, times the derivative of the lower bound. First off, let's look at this. The derivative of any constant is 0. This whole thing goes to 0. The derivative of x is 1. So all we have is this, just as we did the long way. That's only in the circular argument. We use the second fundamental theorem of calculus. Let's try it one more time. Here's number 87. It's actually one of your homework problems. So was 81. I'm doing 2 of your homework problems. Your homework was 81 to 92 all. 87, it says that capital F of x is equal to, from x to x plus 2, of 4t plus 1 dt. So let's define this first derivative. Again, that's a capital F. Sorry about that. So I'm going to do it the long way, and then I'm going to use what I want you to use. I don't want you to do it the long way. I want you to use the second fundamental theorem of calculus. I just want to prove it to you, though. So to find this original derivative, I need to do integration. So I'm going to increase that power by 1 and divide by it. Increase that power by 1 and divide by it from x to x plus 2. I'm going to clean that up. That's 2t squared plus t from x to x plus 2. Now I'm going to proceed to substitute an x plus 2 in for these two t's, minus, then substitute in the x. So there's 2 times x plus 2 quantity squared plus x plus 2 minus, now just put in the x, 2x squared plus x. So x plus 2 quantity squared is x squared plus 4x plus 4. I went and just took that out of the parentheses, didn't do anything else. Now I'm going to distribute that 2 to everything inside of here. It's 2x squared plus 8x plus 8. And then I just proceeded to write all of those terms down, distributed that negative. And then this cancels with this. 8x, 9x, back to 8x, and then 8, 9, 10. And now I'm supposed to go and, what did they want me to do after I found f of x? Find the first derivative. Well, the first derivative of 8x plus 10 is 8. Now let's use the second fundamental theorem of calculus. They want me to find the first derivative. And so here is this circular argument. So how do I do that? I take this function, and wherever I see a variable, I substitute in the upper bound, times the derivative of the upper bound with respect to x, minus take this function and substitute in the lower bound, times the derivative of the lower bound. So let's see, that's 4x, that's 8 plus 1, that's 9. And then the derivative of this is going to be just 1. 1. Here's the minus. This derivative of x is also just 1, so it's just 4x plus 1. I'm going to distribute the negative to the 4x and the 1, and I get 8. Done. Because this is a direct answer to the first derivative. That's it for this video. I'll be recording the next two right after this.